Our next step in addressing ultraviolet disinfection is to consider the approaches we use to describe the kinetics of photochemical reactions. The idea here is that if we can identify those methods that we use to describe the kinetics of photochemical reactions, we can then apply that same logic to describe the kinetics of a photobiological process, specifically inactivation of microbial pathogens using UV radiation. This approach is borrowed from the approach that was presented previously, whereby we apply the logic that's used to describe the kinetics of elementary chemical reactions to predict the rate at which chemical disinfectants, such as chlorine, will inactivate pathogens. I'll start by reviewing the approaches we use to describe the kinetics of elementary bimolecular chemical reactions. The standard nomenclature to represent an elementary bimolecular reaction looks something like this, indicating that molecules A and B will collide to yield a product C, and this reaction is characterized by a rate constant indicated by lowercase k. The standard approach to represent the rate expression for this reaction is described here, where R defines the intrinsic rate of the reaction, which also represents the rate at which the molar concentration of one of the reactants, here described by A, changes as a function of time. And that rate can be described by the product of the rate constant and the activities of the participating molecules A and B. Activity of A and B, described here by the letter surrounded by a square bracket, can be viewed as a representation of the availability of A and B to participate in a reaction, or in other words, the availability of A and B to collide with each other. The rate constant for this expression can be decomposed, and that decomposition allows us a better understanding of the kinetics and the mechanisms of this process. So here is the standard decomposition of the rate constant. It's described as the product of a pre-exponential factor, P, and an exponential function that has the activation energy divided by the product of the gas constant and absolute temperature. By substitution, then, we can describe the overall rate expression like this, and that again allows us to gain a better understanding of the mechanics of this process. Specifically, the product P, the pre-exponential factor, times the activities of the participating reactants describes the rate at which those reactants collide with each other. The exponential term then describes the fraction of those collisions that are successful. The extent of a chemical reaction, as described using this approach, then, is governed by reaction time. In other words, time becomes a master variable in describing the overall behavior of this system. Here's also a standard representation of the reaction progress that we describe using this approach, where the activation energy represents a barrier to the overall progress of the reaction that must be overcome. That barrier is overcome by the energy that's imparted by the two molecules colliding with each other, allowing for bonds within one or both of those molecules to be bent, thereby allowing formation of a new bond and a new chemical. We'll apply similar logic in describing the kinetics of a pure photochemical reaction. Here's the standard nomenclature for a pure photochemical reaction, here indicating that molecule A is absorbing the energy of a photon, described by the product H nu, to yield some product we'll call B, and the rate constant for this reaction is again described by lowercase k. Following similar logic to what was described on the previous slide, we can describe the intrinsic kinetics of this reaction, which represents the rate at which the reactant molar concentration changes as a function of time, and that rate can be described as the product of the rate constant times E, which is the fluence rate, times the activity of the molecule participating in this reaction. So the new term that's introduced in this expression is E, which represents the fluence rate, and that can be viewed as a representation of the availability of photons to participate in a reaction. Again, going back to the Stark-Einstein law, we know that there's an equivalence between molecules and photons in participating in photochemical reactions. So if we're going to describe their kinetics, we have to have a term to describe the availability of photons to participate in the reaction. And that term is the fluence rate. The rate constant, as before, can be decomposed. In the case of a photochemical reaction, that decomposition looks like this. Let me take a minute to describe the terms that comprise this decomposition. The symbol epsilon, with the symbol lambda in parentheses to indicate wavelength dependence, describes the molar absorption coefficient of the molecule, in this case A. The physical interpretation of that is a representation of the availability of a molecule, in this case A, to absorb a photon at a given wavelength, in this case lambda. So it describes the ability of a molecule to absorb photons. The next parameter in the equation that appears here in the denominator is the energy per Einstein at a wavelength, and that's described in the previous lecture. And then the last term that's been presented here is the so-called quantum yield, phi, again, which is a function of lambda. The quantum yield, phi, represents the ratio of the number of molecules of product formed by a photochemical event to the number of photons absorbed. Again, there is an equivalence between molecules and photons in this process. We can then substitute this decomposition for the rate constant into the overall rate expression, and it looks something like this. Going forward then, it's important to recognize that we can describe an incremental dose, dd, by the product of the fluence rate and some short increment of time, dt. If we do that by simply moving E over to the denominator on the left side of this expression, then we get an equivalent rate expression in which the rate of the reaction is now described as a function of dose. It's important for us to understand, then, that the extent of a photochemical reaction is governed by the dose or fluence of radiation delivered to the target, and that dose then becomes the master variable that describes the extent of the reaction. Now, in making an important distinction here, you may recall that in the case of an elementary chemical reaction, the master variable is time, but in a pure photochemical reaction, the master variable is dose. To reiterate, photons and molecules are equivalent participants in photochemical reactions, and so we need to include terms that describe the availability of both to participate in this process. The local rate of a photochemical reaction is then going to be governed by the local values of the fluence rate and the activity of the reactant molecule. That's important because the values of this local fluence rate and the local concentration of the reactant will often show very strong spatial gradients within photochemical reactors, and what that tells us is that the local rates then of photochemical reactions can show remarkably strong spatial gradients. Lastly, this implies that because there are these very strong spatial gradients in the rates of photochemical reactions, overall process behavior in photochemical reactors, including those that are used for disinfection, is strongly influenced by transport behavior and mixing. It turns out that photochemical reactors have a wide range of applications. In the context of this course, the primary focus will be on disinfection, specifically disinfection of aqueous liquids like water and wastewater. And those systems can take on a variety of different configurations. Here's an example of one system that's enclosed. UV radiation is also used for disinfection of air and surfaces. So here's a cartoon representation of how UV radiation is used to disinfect indoor air. And here's an image that illustrates the use of UV radiation to disinfect surfaces, specifically on N95 masks. UV radiation is also used for pure photolysis. A common example in the context of water and wastewater treatment is photolysis of nitrosamines like NDMA. It can also be used for promotion of radicals or reactive intermediates, and those in turn can initiate advanced oxidation processes or AOPs, and more recently people have discovered the use of UV to promote advanced reduction processes or ARPs. Those reactors oftentimes take on a slightly different configuration to allow the introduction of chemicals immediately upstream of the UV irradiated zone. And then lastly, UV is commonly used for photochemical curing, oftentimes resulting in the formation of polymers, which changes the fundamental chemical and physical characteristics of the photochemical target. Summarizing, The logic used to describe the kinetics, or more specifically the intrinsic rates of photochemical reactions, is analogous to the logic that was used to describe the kinetics of elementary bimolecular reactions. However, we need to introduce a new term to account for the availability of photons, and that term is the fluence rate. UV dose, as opposed to time, is the master variable in photochemical reactions. Photochemical processes accomplish changes in biological or chemical constituents following fundamentally different mechanisms than other processes. As a result, photochemical reactors are used for a wide range of applications, including disinfection of various media, pure photolysis, promotion of radical-mediated processes, often leading to oxidation or reduction, and lastly, photochemical curing.